In this video, I'd like to go over an introduction to trigonometric identities. The thing about trigonometric identities is usually when you get to them in a trig class, it's where the concepts of algebra that you might be used to start to merge a little bit with trigonometry. And then specifically talking about identities, the idea is that because the 6 trig functions are so related, what happens is that there's this phenomenon in trigonometry where a lot of things will look different, but they'll actually be the same thing. Even from the fact that sine of theta is the same thing as 1 over cosecant theta. It's saying that those trig functions are related, and so they're actually the same thing. And that can extend to a lot of different identities as well. The first one I want to look at is probably the most important, and it's the Pythagorean identities. So they're based off of the Pythagorean theorem. So I've got a right triangle over here, and the Pythagorean theorem is x squared plus y squared is equal to r squared. And if we think about this in terms of the unit circle, it's the same thing, the same identity, but r would be equal to 1. And so we could write that as x squared plus y squared is equal to 1 squared, which is the same thing as 1. So again, that's just the Pythagorean theorem. But if we recall from our definitions of the trig functions based on the unit circle, x is where we get our cosine value. So cosine of an angle is equal to x, and sine of an angle is our y value. If we plug that into the Pythagorean theorem, we get that cosine squared plus sine squared is equal to 1. So this is the first Pythagorean identity, and so it falls just from that Pythagorean theorem. And the way that it's written in the formulas is usually written with an x value instead of a theta, and that's okay too because we can really put in whatever variable that we want. But I'm just going to go ahead and rewrite it the way that the formula is usually presented, which is cosine squared of x plus sine squared of x is equal to 1. So this is the first Pythagorean identity. So you do need to memorize the Pythagorean identities. There are 3 of them. I like to show where this first one comes from so that maybe you could plug it in if you've forgotten it, just based on the Pythagorean theorem. And then honestly, I recommend not memorizing the other 2, but knowing that you can derive them from this original one. So the way that you get one of them is you can actually divide both sides of the equation by cosine squared of x. So if I divide both sides by cosine squared, that basically means I'm dividing everything on the left by cosine squared and everything on the right by cosine squared. And this is just a rule of algebra, right? I can divide everything on the left side of an equation by a number or variable as long as I do the same thing on the other side. And then if I rewrite this, that will be our next equation. Cosine squared over cosine squared is just going to be 1 plus sine squared over cosine squared. Well, if we remember that tangent is equal to sine over cosine, that means that tangent squared is sine squared over cosine squared. And then 1 over cosine is secant, so I'm going to write this as secant squared. That's the second Pythagorean identity. Now to get the third one, you can divide everything by sine squared. And then we'll just go ahead and simplify it. So cosine over sine is cotangent, so that's going to be cotangent squared. Sine over sine is going to be 1. 1 over sine is cosecant, so that is going to be cosecant squared. And these are our 3 Pythagorean identities. So you really need to know all 3 But again, I recommend only memorizing the first one and knowing that you can just use division to get to either of the other ones. So here's a list of what's considered the fundamental trigonometric identities, and these are the ones that you really need to memorize. So the reciprocal identities are when you have 1 over the trig function, and then the quotient identities really only refer to tangent and cotangent because they can be written based on both cosine and sine. And then finally, the Pythagorean identities. One thing I want to note, we do see the Pythagorean identities a lot if you're studying trigonometric identities. So in general, I would say if you're working on a problem and you see a square in there, chances are you're going to need to use the Pythagorean identity or one of them. And I've got them all listed here, but just know that these are equations that you can move things around. Like for example, 1 minus cosine squared doesn't look exactly like that identity, but it's got a cosine squared in there, it's got a 1 in there, and so you could rewrite this equation. So in this case, what I could do is I could subtract cosine squared from both sides. So that equation, that identity, is the same thing as sine squared is equal to 1 minus cosine squared. So then I know that 1 minus cosine squared is equivalent to sine squared, and I can rewrite it like that. Let's look at this next one. Secant squared minus tangent squared. It's like, okay, I see the squares, so that should kind of trigger your thinking of Pythagorean identities. And so if you look at the 3 identities, okay, let's look at the secant and tangent one. So there is one that relates secant and tangent together. And we could rewrite this equation to simplify the expression we're given. So secant squared minus tangent squared, it looks like we could go ahead and subtract tangent squared from both sides. So that from that identity, we also know that 1 is equal to secant squared minus tangent squared. So I could say this is equivalent to 1. Okay, so let's look at some other examples of things that you might do with identities. One is really just simplifying. Because sine and cosine and all the other trig functions are so related, most likely we can take an expression like this and simplify it to something smaller. And one way that we can do that is by converting everything to sine and cosine so that we can see how they are related. So sine of t is already as a sine, so I'm going to leave that one alone. Plus cotangent, this is where we can use one of the quotient identities. So cotangent is the same thing as cosine over sine. So I'm just going to rewrite it like that, times cosine. And I'll leave that one alone. And so we want to remember at this point all of the regular rules for algebra. And that's what I'm going to be kind of talking about a lot in the next few examples. So here some things to think about are, well, okay, cosine, that's not a fraction, so I could always make it a fraction so that I could combine these terms together through multiplication. So I've got sine of t plus this becomes cosine times cosine, which I'm going to write as cosine squared over sine. Another rule for algebra, oops, I guess I don't want to forget the t, is getting common denominators. So I can see here I've got one fraction, the other one's not a fraction. So again, I can go ahead and make it a fraction by just putting it over 1. I can get a common denominator here. And so in order to get the denominator of sine of t, I can multiply this one by sine of t over sine of t. So that fraction becomes sine squared of t over sine of t plus cosine squared of t over sine of t. And again, another rule from algebra is that I've got 2 fractions here. The fractions have the same denominator, which means I can go ahead and combine the numerators together. Sine squared t plus cosine squared t over sine. So I've simplified it to a single fraction. What to do now to simplify? I mean, some people might be tempted to split it up into two separate fractions, maybe, but that just sort of gets you back to where we had just been. But at this point, this is kind of where I was saying, whenever you see a square, think Pythagorean identity. So if you go back and look at the Pythagorean identities, this is actually the same thing as a 1. So I can replace it with a 1. So this is 1 over sine of t. So it's definitely more simplified than what we originally started with. We are asked in this example to write it with no fractions, and so that's just going to be one more step here because I can use the reciprocal identity. So 1 over sine of t is the same thing as cosecant of t. Okay, let's look at another example. Again, thinking about what we know from algebra, now that we're dealing with trig functions, we can still do multiplication the same way that we would do multiplication without trig functions. So this is a case where we could distribute if we wanted to multiply this through. So for example, I could write that as sine of alpha times 1 plus sine of alpha cosine alpha, which gets rewritten as sine of alpha plus sine alpha cosine alpha. Okay, so this distribution works even if we have trig functions. And I don't have an example like this on this worksheet, but we just kind of looked at the rule. You know, this is similar to if you had something like this, for example. You could distribute it through. Also, as a reminder, if you had something like squared, that in algebra, this means that you'd have to multiply it together twice and then FOIL it. And I'm not going to work it out, but the same thing would apply even if we had a trig function in there. So let's say instead we had something like sine of alpha plus 2 squared. This means sine of alpha plus 2 times sine of alpha plus 2. And we could multiply that out by FOILing and distributing, and keeping in mind that when you multiply something like a sine alpha times sine alpha, that becomes sine squared of alpha. So we are going to be using a lot of the algebra rules from previous classes at this point when we're talking about trig identities. Now let's look at another part of algebra that we can also use with trigonometric functions, and that's factoring. So here we want to factor 4 tangent squared beta plus tangent beta minus 3. One thing that can probably help in general with trying to relate trig functions back to algebra is that you can actually make substitutions. So let's say if you're not quite sure how to factor something like this, you could go ahead and make a substitution and say, well, let me introduce this variable x, and I'm going to let that be equivalent to tangent of beta. And then from there, we can actually rewrite our problem to be 4, and then tangent beta squared, now it's going to become x squared, plus tangent of beta will just be an x, and then minus 3. Then you can go ahead and factor this as you might normally factor this. So there's different techniques for factoring. I'm going to show you one technique. Probably the most common is just like a trial and error method where you try to just get right to your parentheses, and if you're comfortable with that, you can go ahead and stick with that technique. I'm going to show you a different way though, which is that you can start by multiplying the first and last numbers together here, which is -12, and I now need to find two numbers that multiply to -12, but that if I add them together, it's going to be +1. And so in that case, you could try different ones. Like, let me just say if I picked ones that aren't going to work out first. Okay, 6 and 2 multiply to 12. If I added them together, it's like one of them would need to be plus and one of them would need to be minus. Since this middle term is positive, that tells me the bigger number should be positive. So I can make it a +6 and a -2. If I multiply them together, I get -12, so that works. But if I add them together, I get 6 plus -2, which is 4. So that doesn't work. So then I would try a different pair. In this case, now let's try 4 and 3. So positive on the bigger number, negative on the smaller number. If I multiply them, I get negative 12. If I add them, 4 plus negative 3 is negative 1. Or I'm sorry, positive 1. So it checks out. So then what you could do is you could actually rewrite your problem. 4x squared plus, and now I'm going to use the 4 and the negative 3 to split up my middle term. So I'm going to say plus 4x minus 3x, and then I put the negative 3, which was already at the end. So it's the idea of you're trying to figure out the best way to split up that middle term so that you can use factoring by grouping to get to your answer. So if we keep going there, factoring by grouping, okay, what can I take out of the first pair? I could factor out a 4x. So that's going to be 4x times x plus 1. And what can I take out of that second pair? I could take out a 3, but if the first term is negative, you always want to take out a negative as well. So I'm going to take out a negative 3, and if I divide those terms by negative 3, I get a positive x plus 1. And the factoring by grouping is that it works only if you end up with these terms in the parentheses being the same. So what I'm doing is technically factoring that out to the front. And then I put my leftovers in the next parentheses, which in that case is 4x minus 3. So again, you may have another technique for factoring, and if you have a technique that works for you, I'd say go ahead and just stick with it. Okay, it's looking a little messy here, so I'm going to erase some of that stuff. Okay, so our answer is x plus 1 times 4x minus 3. That's how we factor it. But let's keep in mind, in our original expression, we did not have any x's. We introduced that. So we don't really have our answer until we go back and substitute back. In this case, replace all of our x's with tangent beta. So the final answer would be tangent of beta plus 1 times tangent, oh, I should squeeze a 4 in there first. 4 tangent of beta minus 3 is our final answer. And just like any factoring question, you could always check your work by multiplying everything through. So if you wanted to check your work, you could multiply or FOIL. And then if you do that, you'll get back to the original expression. Another technique from algebra that I want to talk about is the idea of conjugates. So in general, a conjugate is basically the same if you have two terms in an expression. It's basically just changing the sign in the middle. So if you have x plus y, the conjugate is x minus y. There's a few different places where it can come in handy. It does come in handy with radicals, and so that's called radicals. So if you might try and rationalize a denominator with something like this, you would multiply by the conjugate. It's also used in complex numbers, the complex conjugate. So like if you have something like, let's say 5 plus 7i, that's a complex number, and the complex conjugate would be 5 minus 7i. I feel like conjugates in general are like an algebraic technique that often get forgotten about because we don't use them as often as some of the other ones. But it does typically come up when we're looking at trig identities. So let's go ahead and look at this original problem. We've got cosine of theta over 1 minus sine of theta. So let's say we're trying to simplify this. And I'm going to do an example with conjugates in the identity section that we're going to do on the next example. But here maybe you could look at it as just we're trying to simplify it by multiplying by the conjugate. And by doing that, one thing you're going to see is that we're going to be able to simplify the denominator by doing that. And so in this case, the conjugate, though, if we're looking at the denominator specifically, is going to be 1 plus sine of theta, because that idea of conjugates is that we rewrite the exact same thing, but just either change it from addition to subtraction or subtraction to addition. And now let's go ahead and multiply. The top is just going to be distribution. So that's going to become cosine theta times 1, which is just cosine theta, plus cosine times sine, which I'm going to write out as cosine of theta times sine of theta. In the denominator, we need to FOIL. So let's see, multiply the first together. 1 times 1 is going to give us 1. Multiply the outside together. 1 times positive sine of theta is plus sine of theta. Inside, negative sine of theta times positive 1 is going to be negative sine of theta. And then finally, the last terms together, which is negative sine theta times positive sine theta, which is going to be negative sine squared of theta. And the reason in general we use conjugates is because of what happens right here, is that anytime you multiply by a conjugate, it's this middle term ends up canceling out because you had one that was plus and then one that was minus. So that goes to 0. So if I rewrite it, we have the numerator hasn't changed, cosine theta plus cosine theta sine theta. All over, now it's just going to be 1 minus sine squared theta in the denominator. So at this point you might say, okay, that denominator doesn't actually look simpler than the previous one. Remember our original denominator was 1 minus sine of theta. So at first glance it might not, but the square again should sort of make you think of that Pythagorean identity. And once we use the Pythagorean identity, we will be able to simplify it a little bit. So using the Pythagorean identity, this is the same thing as cosine squared of theta. Remember, the original equation is sine squared plus cosine squared is equal to 1. So we can rearrange that equation by subtracting sine squared from both sides. So now I can replace the denominator with cosine squared. So cosine theta plus cosine sine. Now it's all over cosine squared of theta. How does it help us here? Well, one thing that's nice is that once we have a fraction that has only one term in the denominator, as opposed to our original one, which was 1 minus sine of theta, had 2 terms. Once you have just a single term in the denominator, that actually allows you to split this up into 2 separate fractions, because we've kind of changed it to, the original one had 1 term in the numerator but 2 in the denominator, and now we've kind of flipped it around where we have 2 terms in the numerator and 1 term in the denominator. But if it's flipped like this, that actually allows us to split this up into 2 separate equations. So if I keep going here and split it up, each with that denominator of cosine squared, I could rewrite this as cosine theta over cosine squared theta plus cosine theta sine theta over cosine squared theta. So now I have 2 separate fractions. You might see how we can keep going from here, which is that not using any trig stuff, we can actually simplify just by what we know from algebra, which is that in either fraction now I have a cosine in the numerator and in the denominator so that I can make a cancellation. So on the left, the cosine cancels, and remember, it doesn't disappear completely, it becomes a 1. And cosine squared in the bottom, since that's cosine times cosine, means one of them cancels. So we're just left with cosine and not cosine squared. So that's 1 over cosine theta. And then basically the same thing in the second fraction. One of the cosines cancel here. It's a cosine squared in the bottom. And so that's going to become sine over cosine theta. And for this final answer, I mean, we could write it as its separate fractions like this, or if you wanted to combine it together, both of these are correct. So all I really did in this example was show kind of how to multiply by the conjugate, but we haven't really simplified our fraction, because if you look back at the original one, it's not really that different. But I just wanted to go over this example just to show you how the conjugate works, and then we'll do an example of why we would use the conjugate with verifying identities in the next part of this video. Now let's talk about proving or verifying trigonometric identities. So what we're going to use in this part is we're going to use all the algebraic techniques that we've talked about before, such as multiplying, simplifying, common denominators, multiplying by the conjugate, and we're also going to use the fundamental trigonometric identities. Let me show you what it's going to look like for the verifying identities type of problems. It's basically going to look like an equation. But the thing is that what our goal is really is we're trying to show that this is true, that there is in fact an equal sign there. So because we're trying to show that it's true, we can't assume that it's true. And for that reason, when we're verifying identities, we can only work with one side of the equation at a time. And that means that if we have if we did have an algebra equation that was equal, we could do things like add a number to both sides of the equation, so kind of work with both sides at the same time. But because we're trying to show that the equal sign is true, we can't do that in verifying identities types of problems. So what we can do to show that it's true is one of these two methods here. So method one is you just pick one side of the equation and you basically only work with that one side of the equation until you can get to show that it equals the exact same thing as what's on the other side of the equation. That's method one. So for example, for this problem I have down here, it would be something like starting with just the left side and only working with this until you can show that it gets that it can be rewritten as 2 cosecant of x. Method two is basically that you could work with each side independently and simplify each side, and then eventually show that what you end up with on the left is what you have on the right. Typically, I just use method one. And that's what I'm going to do for example 7. Okay, so I want to verify this identity, so I want to show that the expression on the left is equivalent to the expression on the right. When I choose a side to work with, I typically try to choose the side that looks more complicated, because then that gives me a goal to try and simplify it. And in the process of simplifying, try to get to what I have on the other side. So I'm going to work with what's on the left. And the first thing I would say here to simplify is, well, we have two fractions. We could go ahead and try and get a common denominator and then add together so we have a single fraction. So that's the first thing I'm going to try here. So I'm going to start just by using algebraic techniques. So to get a common denominator here, I look at the denominators, they're not the same. So basically to get a common denominator, I could just multiply by the other denominator. So the first fraction we could multiply by 1 minus cosine x over 1 minus cosine x. The second fraction we could multiply by sine of x over sine of x. So let's try and simplify the first fraction. Well, the denominator is going to be the sine of x times 1 minus cosine x. I'm going to leave that alone. I'm not going to multiply it through, but I will try and multiply through the numerator. And in that case, I would need to put parentheses around and FOIL it out. And that's going to be 1. And then if I do the outside and the inside, it ends up being, in both cases, negative cosine x. So I'm going to combine them together and write that as negative 2 cosine x. And then the negative cosine x times negative cosine x is positive cosine squared of x. Plus, and then the second fraction, the numerator is going to be sine squared of x over that same denominator. So now that we have common denominators, I can go ahead and combine the numerators together. So I'm just going to put that all in one numerator together. So again, everything we've done up to this point has all been algebraic techniques. But at this point, we're going to start simplifying, and we will start using trigonometric identities as well. So here, if you're looking at it, maybe you've seen what we could do, but I just kind of want to show this part of the numerator. Well, we do have a cosine squared plus a sine squared. I talked about if you see the squared, think about the Pythagorean identities to see if you can apply that. So this is the same thing as 1, so I can just replace it with a 1. So that leaves 1 minus 2 cosine x plus 1 over the denominator. And so here we can use algebra again because I have a 1 plus 1, so I can go ahead and combine those together. So that's 2 minus 2 cosine x over sine times 1 minus cosine x. Again, I can use algebra and I could factor out the numerator. So both terms have a 2 that I can factor out. So if I factor out the 2, what's left is 1 minus cosine x. I will say before I go any further, it's really important with trig identities to remember what your goal is. So right now I'm just simplifying, but it is always good to kind of keep checking back to see what you're actually, because you're trying to get a specific answer here. So I mean, you could say the nice thing about verifying identity problems is you know what the answer is. It's just a matter of getting there. So I need to get to that as my answer. So it's just good to check in on that goal from time to time to see if you're getting closer. I mean, one thing that looks nicer so far, is that we've simplified it a little bit. We've got this 2 there, which makes sense because there is a 2 that we need to get in our answer. And so if we keep going at this point, we can simplify more, again, using algebra, because we've got a 1 minus cosine x in the numerator and a 1 minus cosine x in the denominator. So let's cancel that out. So that's 2 over sine of x. And at this point, we're very close to that final answer. So we wanted to get 2 cosecant of x. So you could get to the final answer at this point. Maybe if I tried to stretch it out a little bit, I might rewrite it like this. Just to show here, now we could actually use the reciprocal identity because that's the same thing as cosecant of x. So that we could rewrite as 2 cosecant of x, which was exactly what we had on the right side of the equation. So we verified the identity, and basically all of this work here shows that that expression we started off, highlighted in yellow, is in fact the same thing as 2 cosecant of x. Okay, let's try another one. let's verify this identity. First, I'm going to try and maybe pick which equation I want to start with, or which side of the equation I want to start with. You could start with either one. I mean, honestly, if I started with the right side, I would probably rewrite those both with sines and cosines and then try to combine together into a single fraction using common denominators. So that's one thing that you could do. Or you could start with the left side. So there is no right or wrong answer in terms of which side you start with. Also, it's good to keep in mind with trig identities, there's really no one answer that's correct. There's lots of ways to verify the identity and show that this identity is true. I'm actually going to go ahead and start with the left. There's a reason I want to start with the left for this one. Because when you first look at it, it might look like there's not really much to do. I mean, I have two terms in the denominator, so I can't split these up into two separate fractions. There's no squares, so there's no like Pythagorean identities. If we remember algebra stuff, like I can't try and simplify cosine over sine because that 1 minus sine in the denominator, I can't view the sine as like a single separate term. But this is where I wanted to say to remember the conjugate as an option with these types of identities. So if I don't see much to do here, one thing I could try is multiplying by the conjugate. So I'm going to do that. So I'm going to multiply the top and the bottom by 1 plus sine of theta. So in the numerator, we get cosine theta. I'm going to multiply it through, plus cosine theta sine theta. All over the denominator, we've got 1. And I guess I'll just write it all out this time, just like I did last time. But we get in the middle a plus sine of theta minus sine of theta, so those do cancel out. And then minus sine squared. So if I keep going, just going to rewrite it now. Okay, so I rewrote it. We might be thinking about what to do at this point. Again, the square means think about Pythagorean identities. So that I can rewrite. Since cosine squared plus sine squared is equal to 1, that means that 1 minus sine squared is the same thing as cosine squared. So I can rewrite my expression keeping the numerator the same, but now I can rewrite in the denominator a cosine squared. To keep going at this point, you might see like a common cosine that you can cancel out. I'm going to leave it for right now because instead I'm going to use the fact that I have, a single term in the denominator, so I can separate these into two separate fractions. So I'm going to rewrite it as two separate fractions, and then I'll do the cancellations. Okay, so to do cancellations, that cosine cancels with the square in the denominator. This cosine cancels with the square in the denominator, so we end up with 1 over cosine theta plus sine over cosine. And so now let's go and see, okay, what was the whole point of this again? Let's go back and look at the original problem. So you can kind of see that we're getting pretty close here. We have it separated into two terms, which is what we wanted. Now we can actually apply a reciprocal identity and a quotient identity to get to the final answer. So here we would use the reciprocal identity, and that is the same thing as secant of theta plus, and here we would use the quotient identity to say that that's the same thing as tangent. And this is what we were trying to get. So we've shown that the left side is in fact equal to the right side. Now let's try one more identity example. Now let's try one more verifying identity example. So I'm going to start by picking a side that I want to work with. And for this one, I definitely want to start with the left side, because if I start with the right side, there's not a whole lot I can do to start with there. There's a lot more to do on the left side. So here might be a time where you're not quite sure what to do. You can't split it up into separate fractions yet because you've got more than one term here in the denominator. You might see that the denominator has two terms. So one thing you could do is to try to multiply by the conjugate. In that case, that would be secant x plus 1 to the numerator and the denominator. What I want to do instead, and this is because if possible, I really prefer to work with sines and cosines because I'm more comfortable with sines and cosines. And the nice thing is that any trig function you could get back and write in terms of sines and cosines, so at least then you're dealing with two different trig functions instead of what we have here, which is three different trig functions. So this is always a technique that I would recommend with verifying identities, is first I'm going to try and rewrite things, everything in terms of sine and cosine. So the first one, cosecant, I'm going to use the reciprocal identity. So cosecant is the same as 1 over sine of x minus cotangent x. I could rewrite using the quotient identity. So that's the same thing as cosine of x over sine of x. All over, and then secant of x, I could use another reciprocal identity and rewrite that as 1 over cosine of x, and then the minus 1 I'll just leave as minus 1. All right, so the first thing then, once I do that, I notice in the numerator I've got two fractions. They already have a common denominator, so I can go ahead and just combine them. So that's 1 minus cosine x all over sine of x. In the denominator, I could try and combine those together. They don't already have a common denominator, but I could certainly get one. So I could write the 1 as a 1 over 1. So in order to get a common denominator, the common denominator would be cosine of x. So I could multiply the numerator and the denominator by cosine of x. So in the bottom, that makes it 1 minus cosine of x minus cosine of x over cosine of x. And so rewriting that, I've got 1 minus cosine of x over cosine of x. So it does look a little complicated here because what we're actually dealing with is something called a complex fraction, which is a fraction in the numerator and another fraction in the denominator. And so one algebraic technique we can use here is the concept of multiplying by the reciprocal. So when you do that, first you leave the numerator fraction alone. So I'm just going to rewrite that as 1 minus cosine of x over sine of x. And then you multiply by the reciprocal of the denominator fraction. And the reciprocal just means we flip the fraction. So instead of dividing by 1 minus cosine x over cosine x, it's the same thing as multiplying by cosine of x over 1 minus cosine x. So I could multiply together the numerators and the denominators, but actually instead of doing that, I might notice right away that we have a multiplication problem, which means that I can do cancellations. And I have a 1 minus cosine of x over 1 minus cosine x, and I can cancel that out. And then when I multiply, we've got cosine of x over sine of x. And if we simplify further, again, checking what we wanted to get, which was cotangent x, we're right on track to get to cotangent of x by using the quotient identity. So cosine over sine is the same thing as cotangent. So one thing to keep in mind with verifying identity is that it's not the answer that's important because you're given that. It really is the process of how you can get to that point, and how you can show your steps in your work to show what identities you're using, and also what algebraic techniques that you're using.